Hi there, this video is about the effect of molecular mass of gas and temperature on the rate of diffusion of gases. Molecular mass and temperature are the major factors which affect the rate of diffusion of gases. So in order to explain these factors one by one, let us start. Before explaining the effect of these factors on the rate of diffusion of gases, we have to understand what is the rate of diffusion. Rate of diffusion is actually the number of gas molecules, number of gas particles passing through unit area divided by time taken for the particles to diffuse. Now, in order to understand what is actually the rate of diffusion of gases, let us suppose a container having a gas confined in it. Here is the opening that indicates the unit surface area, means it is unit length wide and unit length in height. These are the particles of gas confined in it. Say for example in unit time that is 1 second. These are the particles which are passing through and diffusing out, and in that particular time, say for example these are 9 molecules. So the rate of diffusion of this gas at the given temperature would be 9 molecules or 9 particles per second. So this is the concept of rate of diffusion of gases. So rate of diffusion is a quantity, whereas diffusion is a process or phenomenon of spreading of particles from region of higher concentration to the region of lower concentration, whereas the rate of diffusion is a parameter. Now, rate of diffusion of gases depends upon two major factors, which are molecular mass of gas and temperature at which the gas is confined. Now, let us explain them one by one. Effect of molecular mass on the rate of diffusion. To understand how the rate of diffusion of gases is affected by their molecular masses, let us perform this experiment. Take a glass tube with the uniform diameter and place cotton plug soaked in concentrated ammonia solution. So this is the cotton plug or cotton wool which has been soaked in concentrated ammonia solution. This is the cotton plug which has been soaked in concentrated hydrochloric acid solution. Now if both these cotton plugs, they are placed simultaneously and then the ends are closed with the help of a stopper, both these liquid solutions would evaporate and their vapors would diffuse towards inside. These are the vapors of ammonia or particles of ammonia, and these are the particles of hydrogen chloride gas. Both these vapors, they chemically react when they come in contact with one another, and we can see that at this particular point a ring of white cloudy fumes is seen, and this is actually due to the formation of ammonium chloride, which is white in color, and its white cloudy fumes appear. So if we mark this point where the ring of ammonium chloride is formed and then measure the distances of ammonia vapors and HCl particles from their respective ends, we can see that ammonia has traveled more distance in the given time than the distance traveled by HCl particles. So it's obvious from this experiment that ammonia particles have moved relatively longer distance in the given time than the molecules of HCl. So from this experiment, it is obvious that different gases diffuse at different rates. It is obvious from this experiment that since ammonia particles are lighter than HCl particles, therefore ammonia being a lighter gas has diffused faster as compared to HCl, which is a relatively heavier gas. So from here we can conclude that lighter gases diffuse at faster rate and heavier gases diffuse at slower rate. From these observations, an English scientist, Thomas Graham, in 1831 proposed a law named as Graham's law of diffusion, and according to that law, rate of diffusion of a gas is inversely proportional to the square root of its molecular mass. So it's obvious from this relationship that lighter gases would diffuse faster. White cloudy fumes of ammonium chloride appear because of the chemical reaction between particles of ammonia coming from this end and particles of hydrogen chloride gas coming from this end. At this point, both these particles they meet and undergo reaction. So ammonia gas particles react with hydrogen chloride gas particles to give ammonium chloride solid, which appears as white cloudy fumes, and in this way, in the tube, cloudy ring of white fumes of ammonium chloride is formed that indicates the point where both the particles of ammonia coming from left and of HCl coming from right have met and reacted. So it's obvious from this experiment that ammonia has covered more distance in the given time as compared to the particles of hydrogen chloride gas. It is actually because particles of ammonia are lighter. Molecular mass of ammonia is figured out as atomic mass of nitrogen is 14 and of hydrogen is 1. Since there are 3 hydrogen atoms, so total mass of hydrogen in one ammonia particle or molecule is 1 times 3. So it is figured out to be 17 atomic mass units. Similarly, the molecular mass of hydrogen chloride gas is determined by summing up the total atomic masses of elements forming this compound. Atomic mass of hydrogen is 1 and of chlorine is 35.5. It is figured out to be 36.5 AMU. So from their molecular masses, it is obvious that ammonia molecules, they are lighter than the particles of hydrogen chloride gas. Because of being lighter, ammonia molecules or ammonia particles move faster and hence have higher chances to diffuse into the other gases. So from this discussion, it can be established that rate of diffusion of gases is inversely proportional to their square root of molecular masses, which is actually the mathematical form of Graham's law. It can also be explained graphically as if we plot a graph of rate of diffusion versus molecular mass of gases, taking rate of diffusion along y-axis and molecular mass of gases along x-axis. This kind of graph is obtained, and this graph indicates that increase in molecular mass of gas decreases the rate of its diffusion. Say for example, we have 2 gases with us, that is gas A and gas B. Supposingly gas A is lighter, means it has a lower molecular mass, and gas B is heavier, means it has its particles more massive than the particles of gas A. And if we plot a graph of their masses versus their rates, we find that, say this is molecular mass of gas A denoted as MA, and this is the molecular mass of gas B, which is a heavier gas. We can see that being lighter, gas A has higher rate, so this is a rate of diffusion of gas A denoted by RA, whereas the rate of diffusion of gas B would be lower. It is obvious from this graph. So graphically, it is also explained that heavier gases diffuse at lower rate, whereas lighter gas particles diffuse at higher rates. Now let us look at the second factor which affects the rate of diffusion of gases, and this is temperature. Effect of temperature on rate of diffusion of gases. Experiments show that rate of diffusion increases on increasing the temperature of a gas. So rate of diffusion of gas particles is directly proportional to temperature. Now let us see what happens when temperature of a gas increases. So on increasing temperature of gas, average kinetic energy of its particles increases, which is according to one of the postulates of kinetic particle theory, that kinetic energy of particles of a gas is directly proportional to absolute temperature. Increase in kinetic energy of particles of gas makes the motion of particles more intense, means on increasing temperature, increase in kinetic energy happens, and that increases the velocity of particles. Due to this, molecular collisions per unit time, which is also called as collision frequency, it also increases. And because of this, colliding and bouncing off of particles with each other becomes more energetic and forceful. Consequently, spreading of gas particles gets more easy and quicker. Opposite happens when the temperature of a gas is decreased. Now, the effect of increase in temperature or decrease in temperature on the rate of diffusion of gas can also be explained graphically as by plotting a graph of rate of diffusion taking along y-axis and temperature of gas, say in degrees centigrade, along x-axis. We get a straight line graph that indicates that on increasing temperature, rate of diffusion of particles of gas increases, and on decreasing temperature, rate of diffusion of particles of gas decreases. For example, say there was a gas firstly at this temperature T1 degree centigrade, and at this temperature the rate of that gas was this much. Say for example it is R1, and when this gas is heated from temperature T1 to T2 degree centigrade in such a way that T2 is greater than T1, we see from this graph that the rate of diffusion of particles of that gas became higher at elevated temperature. If you liked the video, please do subscribe my channel and hit the bell icon so that upcoming video lecture on chemistry may not be missed. Sharing is requested too. Thanks for watching.